Lance Armstrong's team of engineers uses functions to optimize the design of his bikes and helmets for both form and function. Hi, my name is Tom Atwater, and that is what we'll be examining today: functions, their domains and ranges, and composite functions. Let's start with a definition. A function from a set D to a set R is a rule that assigns a unique element in R to each element in D. Now, in this definition, the set D is the domain of the function, and the set R is the range of the function. A common symbolic way to write a function is to write it like this: y equals f of x. And this notation enables us to give different functions different names by changing the letters that we use to do that. Let's look at some examples. Let's take, for each of the following functions, find the domain, find the range, and then draw the graph. We have, in our first example, y is equal to 2 plus the square root of the quantity x minus 1. And our second example is y is equal to 1 plus the quantity 1 divided by x squared. So let's take a look at our first example. Y is equal to 2 plus the square root of quantity x minus 1. We need to find the domain. The domain is going to be equal to all of the numbers that we can plug in for x, and in that case, the domain is going to start at the number 1 and go up through infinity. For the range, of course, the range is all of the numbers that we can get out of this, and given that this particular portion of our function is going to be 0 or greater, then that means the range starts at 2 and also goes through infinity. So for the graph, we start at the point 1, 2, and then draw going out to infinity. All right, so that's the graph for y equals 2 plus the square root of x minus 1. Let's look at our second example, which is y is equal to 1 plus 1 over x squared. The first thing we need to do, of course, is find the domain. So in this particular instance, what you recognize is that we can't put a 0 in for x because that would make it undefined. However, every other number is possible, which makes the domain start at negative infinity, go up to 0, and then start again at 0 and go up to infinity. So that's our domain. And so for the range, what we know is that it will start at 1 and then go up through infinity. And so the graph itself, we will have this horizontal asymptote at 1 and then going up on both sides like this. All right, so the next thing that we want to do is we want to talk about even and odd functions. They have special symmetry, and we're going to look at that definition right now. A function y equals f of x is an even function if f of negative x is equal to f of x. It's an odd function of x if f of negative x is equal to negative f of x for every x in the function's domain. So I think the best thing to do here is to look at an example so we can determine whether the following functions are even, odd, or possibly neither. All right. So let's take a look at the first one. We're going to apply our definition that we just looked at, which tells us that we want f of negative x. And what we want to do is find out if that's either to f of x or negative f of x. All right, so let's take that negative x and plug it into this function. And what we'll see is that it gets squared, turning it back into positive, which means that f of negative x is going to be equal to f of x. So that, therefore, displays even symmetry. Well, what about this particular function? Again, we want to figure out, does f of negative x either equal f of x or negative f of x, or possibly neither? When we plug the negative x into here, what we'll find is that it will not equal f of x, nor will it equal negative f of x. Therefore, this particular function has neither type of symmetry. Now, we will also note that the graph of a function that has even symmetry will be symmetric about the y-axis. And the graph of a function that has odd symmetry will be symmetric about the origin. All right. Also, some graphs come in what we call piecewise functions. So we're going to take a look at a piecewise function. Graph the piecewise function defined by f of x is equal to 3 minus x when x is less than or equal to 1, and it's equal to 2x when x is greater than 1. So let me switch to here so we can graph this. So let's start with the fact that here x can equal 1, which means we get 3 minus 1, which is 2. So we know that we're going to start at the point 1, comma 2. We also know that this has a y-intercept of 3. And so our line for x being less than or equal to 1 is this. Now, for the second part, we know that for x greater than 1, it's going to be the line y equals, or f of x equals 2x, which has a slope of 2. So it's going to start at that same point, but this time it's going to have a steeper slope. And that's a piecewise function because we have two different pieces combined together to give us that graph. Okay, let's look at another example of where we will create the formula of the piecewise function from the graph itself. So I have here for us a graph made of two pieces, and we need to create the formula for that. Well, what we'll notice is that for the first piece, it goes from 0, not inclusive, up to 2 inclusive. And so that part of it would be that f of x will equal, and as I said, it's going to start at 0, not inclusive, and then include 2. And what that looks like is the graph of negative x plus 2. It has a slope of negative 1 and a y-intercept of 2. Well, but what about this other piece? Well, the other piece starts at 2, but it doesn't include the point 2. And it goes up to and includes the point of x equaling 5. Now, this particular graph has a different slope. In fact, the slope of that turns out to be negative 1/3. And if we followed it back to find the y-intercept, that would work out to be equal to 5/3. So that is how we can create a formula for the piecewise function from the graph itself. Now, one particular piecewise function that's important is the absolute value function. So let's take a look at what that is. It's defined by the following formula. Absolute value of x is equal to negative x when x is less than 0, and it's equal to x when x is greater than or equal to 0. let's sketch that graph and see what it looks like. Well, again, it's made up of two straight lines. It's equal to negative x when x is less than 0. So what that would do is start just, actually I'll put an open circle to show that, and then it's going to go up at this angle with a slope of -1. But now for the other half of the graph, it's equal to x when x is equal to 0 and greater than 0. So now I can fill this in, and this time it's going to be going up at this angle. So this absolute value function graph is a piecewise graph because we have negative x on this side, positive x on that side. All right, next what I'd like to do is look at composition of functions. So let's look at the definition here. We say that the function f of g of x is the composite of the functions g and f. The usual notation for the composite function is f with this little open circle right here, f composed with g, which is read f of g. Thus, the value of f of g at x is f of g of x is equal to f of g of x. All right, I think the best way to see this would be to do an example. So for the functions f of x equals x plus 5 and g of x equals x squared minus 3, we want to find f of g of x. All right, so what that looks like then is to take g of x, which is x squared minus 3, and substitute it in for x here. So we will get x squared minus 3 plus 5. And then that all works out to x squared plus 2. So that's what we get when we compose the two functions in the order f of g of x. It equals x squared plus 2. Well, now it's time for you to try a problem. So let me show you on the screen. I want you to take the same two functions, f of x equals x plus 5 and g of x equals x squared minus 3, and this time you find g of f of x. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. All right, let's find out how you did on that problem. So we want to find g of f of x. And that means this time we want to take f of x and substitute it in for x inside of g of x. So that will give us the quantity x plus 5 squared minus 3. We can expand the x plus 5 squared as x squared plus 10x plus 25 minus 3. And then we can combine the 25 and the minus 3 to get x squared plus 10x plus 22, and that would be our final answer. Okay, great. In today's lesson, we learned about functions, their domains and ranges, their graphs, and composite functions. Be sure to work the exercises that your teacher assigns, and we'll see you next time.